All right, welcome back, high school physics. We are starting semester 2, and the first topic we're going to deal with in this semester is forces. And so what I'm going to do is give you a little bit of overview of what forces are, how we define them, the different types of forces, and then we're going to look at what's called free body diagrams. So if you would, I would get out some piece of paper you can take some notes on, and we're going to kind of go through. First thing I want you to do is I want you to look at handout 4.0. This is on Canvas, or if you've been in class, you can just pull it up from class. There's a picture here about free body diagrams. I'm going to get a little more detail here shortly. But one of the things I want to point out here kind of in the beginning of this handout is how we define a force, okay? So if you look closely here, a force is really just a push or a pull on an object, resulting in the object to be interacting with another object. So as in simple terms, a force is just a push or a pull on something, okay? And there's two different types of or categories of forces. We have contact forces, and that's where one object touches another object or is in contact. And then we have what we would consider to be non-contact forces, or forces resulting from action at a distance. Gravity is a good example of that. Two objects that are attracted to each other through gravity, like the Earth being attracted to the sun, that's at a distance that doesn't have contact. So gravity is a good example. Some of the static forces and things we'll get into later in the year, those are also going to be kind of a part of that. But most of what we'll deal with in this unit is going to be contact forces, where you have something pushing or pulling on an object. The only non-contact force we will really deal with in this unit is gravity, okay? I want you to look at kind of this picture below here. One more thing related is I really want you to kind of catch here the units for what we're going to deal with is forces we're going to measure in newtons. And what a newton is, the amount of force a newton is equal to, is if I have a 1 kilogram object and I want to accelerate that 1 kilogram object by 1 meters per second every second. In other words, my acceleration is 1 meters per second squared and the mass is 1 kilogram. That's how much force it takes to get that to happen. And so a newton by definition is a kilogram meter per second squared. You will see capital N for newtons, and that's what we will tack on to most of our times when we're dealing with forces here. And again, when we get into things, we actually will be using kilograms and meters per second squared for the units for mass and acceleration. Okay, I want to move down here to this picture. And very specifically, I want you to kind of see what's going on here. We've got a guy pulling a box, and he's got a string attached to the box, and the box is going across, probably across the floor, or maybe he can't even get it to pull. What we're going to look at here is, in an example like this, we want to represent all the forces that are acting on, in this case, we're going to define the system to be the box. So we want to think about, I am the box, what's happening to the box? Well, if you're the box, you've got a force pulling on you. Because of the guy, you've got a force kind of pulling this direction, okay? And if you look here on the right, there's kind of an F. I'm going to write it up here, but there's a force pulling that way. That's the guy pulling. We could say it's really the string pulling on the box, and so sometimes we will use FT for force of tension. Sometimes we'll use FA as an applied force. We'll talk about that in a minute. But you want to think about other forces that are acting on the box. It's not just the guy pulling the box to the right. There's also the reality that gravity is pulling that box downward. And so we have this downward force, this gravity is pulling that box downward at the same time. And we've got a W here for weight. A lot of times we will use FG to represent force of gravity, which is really what weight is. Okay. But there's a couple other forces that are a little bit more difficult to think about. And one of the forces you have to think about here is that the reason why the box is not falling through the floor is there must be some kind of force upward. We call this a normal force. And this is really the floor must be holding up that box or pushing back against so that the box doesn't fall through the floor. And so there is an upward force on that. And then As you pull the box, it's kind of hard to pull. It's because there's a force of friction this direction that is opposing the motion of the box. So there are really, if we think about it, we've got 4 different forces actually acting on the box. And our goal really is to represent all of those forces in what we call free body diagrams. Okay. Don't worry if you can't draw boxes. Don't worry if you can't draw things. We will make it simple, and I'll show you that here in a second. What I want to do next, and I want to just kind of walk you through the different types of forces that we will be dealing with. I mentioned already the force of gravity, gravitational force. We're going to really use Fg. You will occasionally see W for weight, but Fg is typically what we're going to use, force of gravity. And we'll actually do some calculating of force of gravity here fairly soon. And that is the mass times G. G, you already are familiar with, negative 9.8 meters per second squared. That's a downward acceleration of an object, right? A force you may not be familiar with is called a normal force. And what it means is anytime there is an object resting on a surface, the surface that's in contact with is pushing back on it. And the reason why it's called a normal force is because it's always 90 degrees or perpendicular to the surface that it's in contact with. So if an object is on a flat surface, it really is straight up. But if you look at the example here, so that this normal force here, force of normal from the tire pushing upward, the ground pushing upward on that tire it's what we call a normal force. Okay, but if you notice here on this ramp, since it's a slanted surface, the normal force is actually at a 90-degree angle to that surface. And so instead of it being straight up, it's actually at a 90-degree angle this way, perpendicular to the surface. So that's what the normal force would look like there. Okay. So anytime you have an object sitting on a surface, there is a force pushing back upward or 90 degrees with the surface. That's called the normal force. Okay. And that's what keeps things from falling through the table or keep things from really just falling through the object or whatever it is. Force of friction, we're going to deal with a lot more detail later in the unit. But friction opposes motion. So if an object is moving to the right, you can assume there's friction opposing it in the opposite direction to the left. There will be times where we will say frictionless and you will ignore friction. And there will be times where we'd say, hey, don't forget to include friction. And you will want to put that. That is always opposing the direction of the motion. Okay. Another form of friction we'll talk briefly about is drag. And we'll still call it friction, but that is like air resistance. Or if something's going through the water is kind of pushing against it. And so that is a form of drag. Okay. Let me scroll down here to a couple other types of forces. External forces, anything that's kind of outside the substance. And by the way, a lot of times our external forces, we will just call it an applied force and we'll use FA. If you have a string, rope, or a cable attached, we really more think of it as something being pulled, and we will call that tension. So there's a force of tension acting on an object. So if something is like hanging from a string and things like that. We will get to this. This is a really big point here, is that we will talk about the net force. So if we add all the forces in the X direction or the Y direction, the net force is added together. If there is an overall net force, it will cause acceleration of an object. And we will deal with that. That's really Newton's second law. So we will get into Newton's laws here shortly. But the next thing I want to do with you is I really want to walk you through some examples of free body diagrams. So I would write these down and I want you to kind of follow along with what we're doing here. And we'll do some of these also in class. Free body diagrams, here's the idea is we want to represent the object, the system, and we want to draw any force acting on the object. Okay. So if I have a 65 kilogram person that's sitting in a chair, here's the good news. Is that I am very bad at drawing people, and you might be too. So we're going to represent the person with a dot. And that's good news because I can't draw. Okay. Now, you want to think about if you've got a person sitting on a chair, what forces are acting on that person? Well, first of all, it's pretty obvious that gravity is pulling that person down. And it really is always gravity. Its force of gravity is straight down. So I'm going to label FG for force of gravity straight down. Okay, that would be pulling on the person. But the question is, why is the person not falling or accelerating downward? Well, the chair must be pushing back up on it. So there is a force pushing upward from the chair on the person, and we call that a normal force. Okay, now when we draw that, we want to draw it straight up, and we also want the normal force arrow to represent the size of that force. Well, considering the person is just sitting there and not moving, these two forces, the normal force and the force of gravity, are actually going to be equal to each other. Okay. If one was bigger than the other, then the object would actually be accelerating up or down depending on the bigger force. In this case, since it's just sitting, there is no acceleration. And therefore, you want to make sure that those forces are balanced. So the normal force is equal to the force of gravity. All right, second example here, we've got a 25 kilogram person sitting in a chair. Okay. Now, what forces are acting on the person? Well, the same forces. We've got force of gravity and we also have a normal force. But here's what I want you to catch. Since the person has less mass, there's actually a less force of gravity pulling downward on that person. And so we're actually going to draw a little bit smaller arrow for our force of gravity. And in this case, the chair has to do less pushing up on that person because it has less mass. So we're going to also draw a smaller arrow for our normal force. Again, since this person is sitting, there's no acceleration. So our normal force must be equal to the force of gravity. So we want to make sure that those arrows are the same length. That's really important. Okay. All right. I'm going to move on a couple more examples. As we move down the page here, we've got a car accelerating on highway. Okay. Again, I'm not very good at drawing, so I'm not going to even try to draw this car. All I'm going to do is I'm going to represent the car with a dot. We're going to assume that it's going that direction, the car. Okay. And therefore, we want to think about what forces are acting on the car. Well, there's got to be some kind of force causing it to accelerate to the right. So we're going to use it, and we're just going to say, since we don't know what it is, we're just going to call it an applied force to the right. Okay. And if you think about it, the car is sitting on the ground, right? Is it accelerating up or down? No. So you know that gravity wants to pull it downward. So we do have to consider the force of gravity acting downward on the object. But what's the reason that the car doesn't fall through the pavement or through the street? It's because the street is pushing back up on the car. So therefore, we need another arrow upward. Sorry if my arrows are not perfectly straight lines, but they should be equal to each other and it should be upward. That's a normal force. That's what keeps the force of gravity balanced with the normal force so it doesn't go up in the air or fall through the ground. Okay. Now, one other thing you want to think about is the fact that, yes, as the car is going down the street, there's got to be something that would potentially slow the car down as it moves to the right. Like if the guy took his foot off the gas, the car would slow down, right? So there, we know that there's a force of friction, but important, if he's accelerating to the right, that means the force of friction has to be smaller than our force of applied to the right. Okay. So because there's acceleration in the X direction, our applied force is actually bigger than our force of friction. But in the Y direction, the up and down, our normal force is still equal to our force of gravity. So I'm writing these out to the side because you're going to kind of have to get used to comparing the two forces, the up and down forces and the left and right forces. A car sliding to a stop. Okay, if it's sliding to the stop, again, we're going to draw a dot. We're going to assume that's the car. Well, let's go with the easy ones. Is there a force of gravity? Absolutely. A force of gravity is downward, right? And we have a normal force of the street pushing up on it, upward. Okay. What is causing the car to stop? Well, think about putting your foot on the brakes and you lock those wheels. There's going to be increased amount of friction. So we know we're going to have a lot of friction causing that car to stop. But if you've taken your foot off the accelerator, there really is not an applied force anymore to the right. This is a little bit confusing sometimes. The car is still moving to the right, but there's actually no force to the right. There's only a force of friction to the left, which is actually going to cause it to slow down. So in the X direction, the only force is the force of friction, and that's what's going to get it to slow down. In the Y direction, your normal force is still equal to the force of gravity. Okay, so those are the only forces acting to get that car stopped. Okay, all right, I've got two more quick examples for you. A ball rolling up a hill, and then we have a boy sledding down the hill. So we have to deal with the fact that we are going to deal with non-flat surfaces. So we've got a ball that is kind of rolling up a hill. So what do we want to do? We want to represent a dot for the ball. Okay. What forces are acting on the ball? Well, force of gravity is always straight down, right? So we have a force of gravity acting downward on the ball. What about the normal force? We do know that there is a force that's perpendicular to the surface. I'm going to kind of draw over here. We do know that at a 90-degree angle with that surface, there is a normal force that's pushing upward on that ball. So what we have to do is we kind of have to, sometimes we just put a dotted line here to kind of imagine the ramp. And then we're going to go perpendicular and we're going to put our normal force on there. Okay. Now, is there any other force acting on the ball? And some of you are thinking, well, yeah, there's a force to the right. Here's the question. Do you have any reason to think that something is still pushing on the ball? Probably not. Somebody at some point let go and the ball is rolling up the hill, but there's no longer actually a force acting on the ball up the hill. Otherwise, it would just continue and continue forever. But we know that that ball is going to slow down. Friction is opposing it. And so therefore, opposite of the up the hill, we have a force of friction down the hill that we're going to label. Okay. So those are actually only the three forces acting on the object. Okay, now we will get into a little bit more detail the fact that these do not all line up with each other in terms of the X and the Y axis. We will have to kind of tilt and do something a little different and break things into components using trig. We're not there yet. Okay, but I want you to see that those forces, there's three there. You do not have an applied force, even though it's still going up the hill. All right, and boy sleds down the hill. For some reason in physics, we always tend to go down is to the right or up is to the right. Let's say this person is riding on a sled downhill. That's about as good as I can do in terms of drawing. Please don't judge. That is my person sledding down a hill. All right, we're going to assume frictionless, which is awesome because it's a sheet of ice. It's probably just zooming down the hill. To represent, again, the person in the sled, force of gravity is straight down, right? Do we have a normal force? Absolutely. The surface is going to be pushing upward in that direction. So we're going to angle it this way. Normal force pushing upward. Guess what? That's it. There's no friction and therefore there's nothing opposing the motion. Now, what is really causing the person to sled down the hill? Well, there's a portion of the force of gravity. If we were to think about gravity and we were to kind of break things like trig triangle, there's actually, based on this angle here, we would have an FGY component and an FGX component of the overall force of gravity. That's where we eventually are heading with this. And so there's a little piece of this that's causing that to accelerate down the hill. There's your intro to free body diagrams and forces. We're also going to do some of this in class. So I hope that's enough for you to get a big picture of what we're doing. And there you go.